In this short video, we're going to be discussing one quick example of a strange vector space. For our set V, we're going to take the set of all positive numbers in the real line. So excluding 0 and the positive numbers. Now pay attention, we're going to define addition and scalar multiplication in a very non-standard way. When we take two vectors and add them together, how we're defining this is we're going to multiply together the two numbers x and y. So in the notation I've written here, we're thinking of a positive number simultaneously as a vector and also as a number. If you add together two vectors, and that means multiplying the positive numbers, you're going to get another positive number. And so that will still be in the set V. For scalar multiplication, we will exponentiate. So if we take a scalar times a vector, that's going to be defined to be the number x to the cth power, which will also be a positive number, and therefore a vector in this space. So a good question to ask yourself is, what is the 0 vector in this space? Well, in this funny space, 0 isn't 0, 1 is 0. Let's think about what the 0 vector should be and how it should behave. The 0 vector should have the property that when you add it to something, it doesn't change that thing. But here, addition has been defined in a strange way. If you take the vector x and you add it to the vector 1, the definition of addition in our space says that you should multiply x times 1. And you get x back, which is still the vector x. So 1 is really behaving like the 0 vector. Now, I encourage you to go through this vector space for practice and check all 10 of the axioms to prove that it's really a vector space. And you may find some of these on your homework. But I'm going to check some of the axioms right now. The first axiom is that when you add two vectors together, you better get a vector in your space. So this should be clear from the definition of vector addition. When we add together two vectors, we multiply x and y. X and y are both positive numbers. And so x times y, being a positive number, is also a vector in this space. This is also a check for axiom number 2, by the way. Axiom number 2 is the statement that addition should be commutative. So x times y is equal to y times x. And that means that x plus y as a vector is equal to y plus x, making addition of vectors commutative. Another axiom we're going to check right now is that of additive inverses. Normally when we think of additive inverses, we use the negative sign. X plus minus x equals 0. Those would be vectors that are additive inverses of each other. But here, what is the additive inverse? Addition isn't addition, it's multiplication. So for this space, the additive inverse of a vector x, which in vector notation would be denoted minus x with a hat on it, is going to be given by the number 1 over x. Because if you take the vector x plus its additive inverse, by definition, you will be multiplying the numbers x times 1 over x, which gives you the number 1. And the number 1 in our funny space is the 0 vector. So the additive inverse of a vector x is going to be given by the number 1 over x. Axiom 6 tells us that we should check whether scalar multiplication as defined is giving us a positive number. A scalar times a vector is defined to be the number x to the cth power, which I have here in vector notation, or we can just write the number x to the cth power. So you just need to convince yourself that this is indeed a positive number. If c is equal to 0, this is going to be x to the 0, which is 1, a positive number. So if c is equal to 0, you get x to the 0, which is 1. That's positive. If c is a positive number, no problem. X to the c, the power is going to be positive. And if c is a negative number, just remember your rules for exponentiation. X to the c is 1 over x to the negative c, which is then that positive number, and this is positive. So it's certainly closed under scalar addition as well. Let's look at one of the distributive laws. These are all pretty fun to check. So axiom number 8 is a distributive law. We want to know that if we have two scalars that we're adding together inside of parentheses times the vector, that we get cx plus dx. And we just have to be careful about the rules that we're using. So scalar c plus d times the vector x would be defined to be x to the c plus dth power. Exponentiation rules tell us that this is x to the c, x to the d. And this then is the sum of two vectors, because vector sum is carried out by multiplication. So this is really cx plus dx. Let's check two more axioms and then I'll leave the rest to you for exercises. Axiom 9 is a kind of associative rule for scalar multiplication, we would want to know that if we had a scalar and then parentheses, scalar times vector, that's equal to the scalars being multiplied together first and then being multiplied to the vector, rearranging the parentheses. And this is going to come down to another one of your rules for exponentiation. And then the last axiom deals with multiplication by the scalar equal to 1. 1 times a vector x is defined to be x to the 1th power, which is, of course, still going to be x, working out as it should. Now, I may have lost track here. I believe there are a couple more axioms left to check. We did 1, 2, 5, 6, 8, 9, and 10. And if you check the remaining few axioms, then you will have assembled a proof that this strange space really is a vector space.